Hello, and welcome to the Abbey Road Observatory. I'm Jim, the filter guy. We are in my backyard in the middle of a fairly large city. And as you might imagine, my skies are not dark. And that is the topic of today's video. I am going to give you a couple of different ways to evaluate just how dark your observing location is and compare it to mine. I also explain a method that I came up with to measure the spectrum of my backyard light pollution, which is pretty important for all of my filter evaluations. Anyway, let's carry on with today's video titled Measuring Backyard Light Pollution. Hello, and welcome to today's video, Measuring Backyard Light Pollution. This is a topic that is very closely related to my main area of interest, filters. To be able to understand how filters work and how to choose the best one, we have to have a solid handle on the nature of the light pollution we are fighting. Let's begin by having a look at the view from my Ottawa, Canada backyard. I live in the middle of the city, so even on a good night, I can see only a few dozen stars. On a bad night, I can't see any stars at all, just the moon and the planets. But that is just my own personal perception of the night sky. I wonder how bad my skies are compared to other locations. To be able to compare my sky brightness to others, I need some sort of metric. Enter the Bortle scale. The 9-step scale was first proposed by John Bortle in the February 2001 issue of Sky and Telescope magazine. He proposed it as a way of comparing the darkness of different observing sites. Each of the 9 steps in the scale are defined by the extent to which stars and deep sky objects are visible to the naked eye. Use of the scale has become quite common, with many astronomers using it as a way of evaluating the darkness of their sky and comparing it to that of fellow astronomers. Because the scale is based on the perception of the individual observer, it is a rather subjective way of evaluating sky darkness. Nonetheless, it is a very popular scale. Numerous sky darkness maps can be found online that use the scale. These maps are based on satellite data or from ground measurements. This example is for the part of Canada where I live, between our 2 largest urban centres, Toronto and Montreal. Based on this map, that is from 8 or 9 years ago, most of Ottawa has Bortle 8 to 9 skies. If I wanted to observe under Bortle 2 skies, I would need to drive about 90 minutes from the city. As I mentioned earlier, the Bortle scale is completely subjective. A less subjective but still human observation-based method of evaluating sky darkness is something called the naked eye limiting magnitude. The method is very easy to do. You start by going outside, letting your eyes become dark adapted, and then you look up. Find the faintest star you can just barely see with direct vision. Then, locate that star in a star chart or planetarium software on your mobile device and determine its magnitude. This is very quick to do, and you can in fact do this periodically throughout your night to keep track on how sky conditions are changing. The method does not rely on electronics, although finding a star's magnitude using a planetarium app is more precise than using a printed chart. Normally, this method assumes that the star you use is from directly overhead, in the area of the zenith. With practice, you will get to know the magnitude of a handful of reference stars, and will be able to quickly evaluate the sky darkness without the use of a chart. Although this method is less subjective than the Bortle scale, it is still dependent on the visual acuity of the observer. If you instead want a completely objective evaluation of your sky's darkness, you will need a sky quality meter. A sky quality meter, or SQM for short, is essentially a calibrated brightness meter, similar to the exposure meters that photographers used to use in the olden days. The image here is of the most common brand of SQM. It is roughly the size of a deck of cards. The device measures the brightness of the sky in units of magnitudes, or mags, per square arc second. The use of the term magnitudes here is the same as the magnitude scale used to quantify the brightness of objects in the sky, such as the stars and planets. A larger value of mags per square arc second means a darker sky. SQMs are relatively inexpensive, being in the $150 Canadian range. As the sticker in my image implies, the most popular SQM on the market is made by a Canadian company called Unihedron. I have used my SQM to measure the darkness of my backyard on numerous occasions. This plot is a summary of the range of readings that I have recorded over the past few years. I have found that the reading varies significantly with the direction in which I am looking, being lower, that is, brighter, when I look towards downtown or in the direction of nearby shopping or sporting facilities. The reading also changes significantly with the condition of the sky on the particular evening. The presence of fog, haze, smoke, or high-altitude ice crystals can all impact how much of the city's light pollution is scattered back towards the ground. There is always a variation with elevation angle, which is related directly to how much atmosphere I am looking through. More atmosphere means more scattering of light pollution. The variation in SQM readings with elevation is higher on nights with bad observing conditions, as illustrated in the plot. From my various SQM readings, my typical backyard sky brightness seems to be in the 16.8 to 17.7 mags per square arc second range. I wonder what that means in terms of the Bortle scale. Luckily, somebody has already worked that out for us. The table shown here compares the three sky darkness measurement methods that I have described. The table can be used to convert between the different scales. Not obvious from the values in this table is the fact that all three scales are logarithmic. A Bortle 4 sky is not half as bright as a Bortle 8 sky. A Nelm 6 sky is not 50% darker than a Nelm 4 sky. To put things into perspective, let's add another column to the table. This one in engineering units of microcandela per square meter. Now we can see the very large range of brightness that we are dealing with, and why using a logarithmic scale is so convenient. The last thing to note before leaving this table is where my backyard sky brightness sits on these scales. Well, not too good, to be honest. My backyard is a solid Bortle 9+, about 20 times brighter than the Bortle 5 skies I enjoy at my cottage in the summertime. With such terrible skies, it is not hard to understand why I have such an interest in light pollution filters. Key to understanding how these filters work is knowledge of what the light pollution's spectrum looks like. The plot shown here is my best guess at what the light pollution spectrum is in my backyard. I have constructed it from the information I have been able to find online in various research papers and textbooks. The spectrum is made up of different light pollution sources. The first being classic outdoor mercury and sodium vapor lighting. Next is newer LED-based street lighting, which most of the city of Ottawa now has. The third main component is naturally occurring sky glow that is emitted from molecules in our upper atmosphere. There is another important natural light pollution source, the moon, but I have not included it in my baseline spectrum construct. Based on the information I could find, I made an educated guess at how to mix these light sources together and end up at the correct integrated sky brightness. I have been testing light pollution filters for over 15 years now, but I had not had an opportunity to confirm by measurement that my light pollution spectrum assumption is correct until the fall of 2021. I had been working at the problem of measuring the night sky's spectrum for quite a while. I made many attempts using my benchtop spectrometer, combining it with different telescopes or camera lenses, but this effort was to no avail, as the signal I was trying to measure was simply too low. The prospect of using a spectrometer suited to measuring astronomical targets was simply out of the question, due to them being way too expensive. Fortunately, I came across a technical paper where the researcher used a telescope combined with a camera and a series of filters to measure a spectrum. I have all of those things. This is an idea just crazy enough to work. The first thing I did was comb through my library of astronomical filters to come up with 11 different passbands, covering the spectrum from near ultraviolet to near infrared. The measured spectra of the 11 filter combinations are shown in the plot on the right. I then set up my 4-inch refractor and aimed it south at 45 degrees up, with the scope well out of focus in order to give a nice uniform image of the sky. Using my monochrome ASI 290 camera, I captured a reference image using no filters, being sure to set the camera exposure time so that the image was brightly exposed, but not overexposed. I then captured an image with each of the 11 filter combinations, using identical camera settings. Finally, I confirmed the spectrum of each filter combination using my benchtop spectrometer, which is the source of the data shown in the plot on the right. With my images collected, the data reduction was straightforward. I knew the percentage of light getting through each filter combo from my spectrum measurements, and the percentage of light relative to the reference frame being picked up by the camera with each filter using my images. From this, I was able to find the relative contribution to the total image brightness from each filter's passband. I scaled the resulting spectrum points uniformly to achieve the best fit with my constructed spectrum that we saw earlier. The plot on the right is the result, the blue dots being my measured values. To say I was pleased with the result is an understatement. My measured sky spectrum matches my assumed spectrum very well, with only a slight overprediction in the near UV part of the spectrum and a slight underprediction in the near IR. In this video, I have shown you 3 different methods of evaluating the darkness of your night sky. Using a camera and filter-based method, I have confirmed that the spectrum of the Ottawa light-polluted sky is consistent with my expectations. This is an important finding for me, personally, as it adds confidence to the filter performance predictions that I make for my particular light pollution conditions. If anyone has any questions, I would be happy to answer them. Feel free to leave your questions in the comment section below, or to email me directly using the address in my channel description. If anyone is interested in learning more about my backyard light pollution measurement, you can find a summary report on the experiment at the ResearchGate link shown here. If you have enjoyed this video, please take a moment to leave a like. If you would like to stay up to date on everything the Abbey Road Observatory is up to, please subscribe to my channel. This is Jim, the filter guy, wishing everyone clear skies.